So as you can see from these different curves here, as you go down into the ground, two things are happening. One of them is the amplitude is decreasing, and the phase shift is changing. So if we go to say 5 feet, the 5-foot curve there, we see that it goes up. It reaches its maximum about in August the 20th. Now the hottest day may be earlier than August the 20th, but at 5 feet that looks like that's about the maximum temperature there. The minimum temperature at 5 feet, it looks like that's around 48 degrees, and that occurs March the 11th. So the coldest soil temperature is out of phase with the coldest air temperature. That's one of the advantages that you have going underground, is this delay in time in which that cold front that you experience up here at the surface is delayed in the earth. And so that is an advantage. The coldest day and the coldest soil temperature do not occur at the same time. Kind of as a guide, you can say that if a blue northern came through, that temperature would be reflected about 4 weeks later if you were at 4 feet. So about 1 week, delay of about 1 week for each depth of soil that you go down to. So, and also these curves are also dependent upon what kind of soil you have. If the soil is drier, well then the amplitudes and the phase shifts will change. Now this one here is defined as a moist soil, and there's a term down there that we'll get into a little bit later. It's called alpha. Thermal diffusivity is 0.6 foot squared per day. Now that is just a measured value that we can either measure by test, or we can measure from, or we can get from soil data that we have in the installation guide. So the amplitude, the annual swing, the phase shift, and the type of soil that we have will need to be identified when we get into the design process and we're selecting values for soil resistance, and we're estimating temperatures throughout the year. Now the different kind of system configurations that we can have with our ground source heat pumps include both horizontal and vertical. And the question a lot of times is asked about this time, well, which one is the best? And my answer a lot of times is the one that you're selling. Okay, if you have a drilling rig, you're probably going to sell vertical. If you have a trencher, you're going to sell horizontal. A lot of times the job site will determine what you can do. You can't trench economically in rock. So a lot of times if you have a rocky location, then you're going to have to drill. If the soil has easy trenching characteristics, and you find a lot of trenchers in your area, you might be going horizontal. Whether you put 1 pipe in each trench, 4 pipes, 6 pipes, 8 pipes, will all depend upon an economic study of seeing what it takes to bury pipe underground in your particular location. Which is best from a thermodynamic standpoint? Not one is better than the other. The vertical borehole will have a higher average temperature than the horizontal system, but remember that whatever we don't have temperature-wise with a horizontal system can be compensated by length. You can make the ground heat exchanger in a horizontal system longer and get the same kind of thermal performance than you can out of vertical. What we want to do is end up picking the one that's the most economic for your location. So if you've got a nice big yard, you can trench in it. If trenching is easy, the soil doesn't collapse whenever you trench through it, then you would probably want to pick a horizontal system. If you've got a tight land area, you don't have a lot of surface area, you want to get in there and get out in a hurry without disrupting a lot of shrubbery and things like that, you may want to drill vertically. When we first started in this technology, we talked about installing one of these systems in 3 days. And now we've written articles in our magazine where we say in by 9, out by 4, meaning that the drilling rig got there by 9 o'clock in the morning, and by 4 o'clock in the afternoon we were out. So whether it's horizontal or vertical, what you need to do is go around and find somebody that's successful and talk to them and look and see what they're doing, and let that be your guide. If you talk with a trencher manufacturer, he's obviously going to want to sell you on trenchers. Drilling people are the same way. Commercial jobs, most of the time, will be vertical, just because of the amount of heat exchanger that you have to have, and you can get more capacity out of a drilled hole than you can than a foot of trench. Now, the heat pump operation is just a lot of fun. You have a refrigerant that's being circulated by a compressor. It is a piston compressor or a scroll compressor. It could be a centrifugal compressor. It could be any kind of refrigerant compressor that's compressing the refrigerant vapor. So whatever comes into the compressor will be a vapor, and the compressor then compresses that, and in the process raises its temperature. Now, in the cooling operation, the hot gas that's coming off of the compressor, in most cases, we say it's optional here in this particular diagram, will go to the desuperheater coil. The desuperheater coil is a coil that now takes water from the domestic hot water tank and circulates it through a water to refrigerant coil, and takes the superheat out of the refrigerant and heats the potable water. Okay, about 10% or 5,000 BTUs per hour is about the maximum capacity. But believe me, you have plenty of hot water coming off of one of these systems. You can make the calculation that if you ran one of these systems 10 hours a day, it was a 3-ton heat pump, 3 ton being 36,000 BTUs per hour. Compressor heat being another 14,000 might make it 50,000 BTUs per hour. That amount of heat would raise 1,000 gallons of water, 60 degrees Fahrenheit in a 10-hour period. So you can see it's a tremendous amount of heat that's coming off of a 3-ton heat pump system. Now that includes all of the heat, and you don't have that much superheat. But that's why some of these ground heat exchangers say, well, why is there so much pipe in the ground? Well, we're handling a lot of heat. You can think about heating 1,000 gallons of hot water every day with a 3-ton heat pump system. That's quite a bit of heat. Now, after the hot gas goes through the desuperheater, it comes out as it still is a hot gas, but not as hot. I know that's not very engineering wise talk, but it comes out of there and it's cooler. But it's still a hot gas. It goes over there to another water refrigerant coil, and this is the ground heat exchanger. And this, in this case, would be the condenser. We're going to condense that hot gas into a hot liquid. And we do that by circulating the water that's in the ground heat exchanger through that coil and removing enough energy from that hot gas to condense it back into a hot liquid or a warm liquid. Depends on your preference. That warm liquid then comes to the expansion device. The expansion device drops the pressure, and as it exits the expansion device in the refrigerant loop, it comes out as a cold liquid. That cold liquid then continues its journey up into the air loop. Okay, so that's the evaporator coil now. So that cold liquid comes into the evaporator. The warm air of the building load then comes across that, evaporates it. That's why I guess we call it an evaporator. Exits the evaporator as a cool liquid, comes down the compressor, or cool vapor, comes down to the compressor, is then compressed again, and the cycle continues. So air that was the return air, which is warm, comes through the evaporator, comes out cool. Now, we normally talk about 4 loops that we have in this particular system. One is the air loop, in which the air is being cooled. That's loop number 1. Loop number 2 in here is the we've got to find this here on the drawing, but loop number 2 is the refrigerant loop. And that refrigerant, like I said earlier, is the loop that the refrigerant is being moved around by the compressor. Loop number 3 is the ground loop, and that's the plastic pipe that we have in the ground hooked up to a circulating pump.